Hi everyone, this is my fourth video in the series of quantum chemistry classes, and in this video we shall learn about application of Schrodinger wave equation for a particle in one-dimensional box, which is mainly considered as an infinitely potential well. And this problem is actually a simplest quantum mechanical problem that mainly represents the translational motion of a particle. And here let us consider a one-dimensional box which is having a length equals to a with infinitely high walls at the two ends. And inside the box the potential energy V will be equals to 0. The reason is the particle is not acting upon any of the force. So that's why the potential energy is taken equals to 0. But at the walls, the height of the walls is very high, infinitely high, and at particular case it is not possible to judge the exact potential energy. Therefore, the potential energy at the walls has been taken as V is equals to infinity. And you can observe inside the box the potential energy is 0, and at the walls the potential energy is equals to infinity. That means the potential energy is not constant or not continuous. There is a discontinuous potential energy because there is a sudden rise in the potential energy, and here the potential energy is infinity. When it comes to inside it is 0. Again when it comes to this end, again the potential energy is infinity. So there is no correlation between the potential energy of the particle inside the box and the potential energy of the particle at the walls of the box. So when you are applying the Schrodinger wave equation for this one-dimensional box, it is better to apply in two cases. In one case, application of Schrodinger wave equation for inside the box, and in second case, application of Schrodinger wave equation outside the box. So now we shall see how the Schrodinger wave equation can be applied for this one-dimensional box in two cases, that is inside the box and outside the box, in particularly speaking on the walls of the box. So case 1. So first we shall go with inside the box. Inside the box. And for this, we shall apply the Schrodinger wave equation. The Schrodinger wave equation for one dimension is given as h cross square by 2m into dou square by dou x square plus potential energy V of xi is equals to E psi. So this is the Schrodinger wave equation for one dimension. Since we are analyzing the Schrodinger wave equation, applying the Schrodinger wave equation inside the box, wherein inside the box the potential energy V of x that's equals to 0, on applying this condition for the Schrodinger wave equation, the equation will get reduces to h cross square by 2m into this term will become 0, so dou square psi by dou x square that's equals to E psi, right? And let me consider this as equation number 1. And actually in this problem we are intended to solve the Schrodinger wave equation for getting the energy of the particle as well as its wave function. The main motto of performing the application of Schrodinger wave equation for the particle in one-dimensional box is to find out its energy and its wave function, and we shall proceed for the same. And now we shall modify this expression dou square psi by dou x square. I have retained this, and this has been cross multiplied so that it will be 2m by h cross square into E psi. So here we have the minus. So 2m by h cross square into E psi plus dou square psi by dou x square that's equals to 0. And now this whole term, that is 2m by h cross square into E, this whole term will be taken as k square, an arbitrary constant. Okay, so by changing this whole term with the term k square, equation will get reduces, that is dou square psi by dou x square plus k square psi that's equals to 0. Let me consider this as equation number 2. And here you can observe the k square is simply a constant and it doesn't have any variable. That means it doesn't have the term x, means the term k square is independent of x. And you can observe this equation dou square psi by dou x square plus k square psi is a second order differential equation. So for that second order differential equation, we can write the solution as psi is equals to a cos kx plus b sin kx. Right, this is the solution for a second order differential equation. Let me consider this as equation number 3. And this is the whole and sole thing we performed for inside the box. And just remember this equation and this equation. There is equation number 2 and equation number 3 provided. Here we have written the value of k square is equals to 2m by h cross square into e. This is the value of k square. Right, and here this is the solution of this second order differential equation. And now we shall apply the Schrodinger wave equation for outside the box. Okay, and for outside the box, so for outside the box, this is the case B. We are applying Schrodinger wave equation for the one-dimensional box for the particle presented outside the box, means present at the walls. And we know that on the walls of the box, that is outside the box, V of x, that is potential energy, is equals to infinity, right? And we can apply this condition for Schrodinger wave equation. So according to which h cross square by 2m into dou square by dou x square plus potential energy V of psi is equals to E psi. This is our Schrodinger wave equation for one dimension. And now we shall apply the condition potential energy V of x is equals to infinity. This term will turns to infinity. So that we can write this equation by modifying to some extent, that is dou square psi by dou x square plus 2m by h cross square into E minus V of psi is equals to 0. So this is the modified form of the Schrodinger wave equation. Here we can apply the term V is equals to infinity. So that dou square psi by dou x square plus 2m by h cross square into E minus infinity of psi is equals to 0. And here we said at the walls of the box where the height is infinite, so due to infinitely large potential energy, it is not possible to, or it is highly impossible to find out the probability of the particle. That means there is no wave function, there will be no amplitude for the matter wave, that is the particle. Therefore outside the box the value of psi is equals to 0, right? So for outside the box, the probability of finding the particle is 0 because of infinite height. For outside the box, there is no resultant wave function, that is psi is equals to 0. When psi is equals to 0, this whole term will become 0. Again dou square psi by dou x square will be equals to 0. Means when psi is 0, just remember psi is equals to 0 when x is equals to 0, at that condition also psi is equals to 0, and as well as when x is equals to a, at that condition, means on the wall of the box again the wave function is 0. And now so we got there is no resultant wave function. So in the previous minute I said we are solving this problem just to find out the energy and wave function of the particle. So now we got there is no resultant wave function for the particle when it is present outside the box. When there is no wave function, obviously the energy of the particle will remain 0. So it is better to find out the energy as well as wave function of the particle inside the box itself. So for inside the box, we already got a second order differential equation, that is dou square psi by dou x square plus k square psi is equals to 0. And for that second order differential equation, we got the solution, that is xi is equals to a cos kx plus b sin kx. So in that equation, that is xi is equals to a cos kx plus b sin kx. And here in this equation we have two terms, a and b. These two are simply the arbitrary constants, and the value of a, value of b and value of k will be determined by applying the boundary conditions. Means whether the value of x is 0 or whether the value of x is a. Okay, so now we shall apply those boundary conditions for this particular equation in order to find out the values of a, k as well as b. And now we shall apply the first boundary condition in case 1, that is at x is equals to 0. And just now we said when x is equals to 0 and when x is equals to a, at both these conditions the value of xi will remains 0. Therefore when x is equals to 0, xi remains 0. We can apply these two conditions for this particular expression, that is solution of the equation. So when xi is equals to 0, let me write in this way, a cos k of 0 plus b sin k of 0, and that's whole and solely equals to 0. And we know that sin 0 will be 0, but cos 0 is equals to 1. So this whole term will turns to 0 and cos 0 will remains 1. So 1 multiplied with a, therefore the value of a is equals to 0. So we got the value of a as 0. And now we shall apply the second boundary condition in case 2. In case 2 we shall apply the second boundary condition, that is x is equals to a. Again at x is equals to 0, the value of wave function xi will again remains 0. Okay, and now we shall consider the same equation, that is xi is equals to a cos kx plus b sin kx, and here we got the value of a as 0, right? So when you apply the condition x is equals to a, xi is equals to 0 and capital A is equals to 0, this equation will turns anyway. So let me write this equation once again, xi is equals to a cos kx plus b sin kx, and here the value of a is equals to 0, this whole term will turns to 0 and xi is equals to 0, so b sin k, the value of x is a, that's equals to 0, right? So b sin ka is equals to 0, or else I can write it as sin ka is equals to 0, or ka is equals to, when sin comes to the right hand side it will become sin inverse of 0, and we are well aware sin inverse of 0 is simply nothing but n pi. So we will be getting the value of k, that is k is equals to n pi by a. So the value of k is n pi by a. Let me consider this as equation number 3. Okay, so the value of k is n pi by a. And now we shall move further to find out the value of the energy as well as wave function of the particle. And now, since we determined the value of a, which is equals to 0, but still we didn't got the value of b, so now we shall apply the same condition. So in that expression, xi is equals to a cos kx plus b sin kx. In this equation, actually the value of a is equals to 0, right? Since a is equals to 0, this term is already turns to 0, and now we shall turn psi is equals to b sine, already we got the value of k is equals to, the value of k is equals to n pi by a, right? So the value of k is n pi by a. So b sine, that the value of the value of k, n pi x by a, and this is the equation for wave function. And we already did in equation 2, I think. From equation 2 we determined the value of k square, that is k square is equals to 2m by h cross square into a, and here we have the value of k is equals to n pi by a. So we can convert this into k square is equals to n square pi square by a square. So here we have k square, here also we have k square. We can compare these two terms so that it will be 2me by h cross square, that's equals to n square pi square by a square. Since our main intention is to find out the energy of the particle, so E energy is equals to n square h cross square pi square by 2m a square. This is the whole and soul term for energy of the particle present in one-dimensional box. And since we have the value of h cross, since h cross is equals to h by 2 pi, we can alter the expression by inserting this. So E is equals to n square pi square, h cross is h by 2 pi. So here we have h cross square, so h square by 2 pi square, right? So 2 2s are 4 actually, 4 pi square into 2 m a square, and here pi square will get cancelled, so whole and solely E is equals to n square h square by 4 2s are 8 m a square. This is also the expression for energy of the particle in one-dimensional box. So you can remember these two expressions for the energy of a particle in one-dimensional box, which is mainly asked in any of the competitive examination like IIT JAM or in CSIR NET or in terms of or in GATE examination also. So here the value of n can take the integral values 1, 2, 3 and so on. And this equation, let me take this as equation number 4. This equation will actually represents the energy of a particle present in one-dimensional box. Okay, and now we have determined the energy of the particle. Since we have to get still we have to get the wave function, that is xi, the value of xi for the particle, and the total probability of finding the particle within the box. See, xi will actually give the wave function, but if you want to find out the particle, the probability of finding the particle will be given by the term xi square. The square of the wave function will actually gives the probability of finding the particle. So if you want to get the value of exact wave function, we are supposed to take the integral of this xi between the limits 0 to a, between the limit 0 to a, and xi square, since for the one dimension, so it is xi square x into dx, and the total probability for finding the particle within the box will remains equals to unity. Therefore integration of 0 to a into xi x square into dx will be taken equals to 0. But here we said xi is equals to b sine n pi x by a, right? So we can use this term over here so that we can write in this way, since xi is equals to b sine n pi x by a, we can insert over here between the limits 0 to a b sine n pi x by a whole square into dx, right? So here it will be b square, let me take that to the outside, so 0 to a sine square n pi x by a into dx. Right, so sine square n pi x by a into dx. But we well aware that sine square theta is equals to 1 by 2 of 1 minus cos 2 theta. This is in terms of integration. Sine square theta is equals to 1 by 2 into 1 by 2 of 1 minus cos 2 theta. We can apply this particular condition for this sine square n pi x by a. So when you apply the same, the equation will get changed as integration of b square is already present outside, that is so b square of between the limits 0 to a, and here the term will get changed half of 1 minus cos 2 n pi x by a into dx. Okay, that's equals to 1. And now we shall perform the integration of this one. So b square will be outside. So here we have to multiply the dx. So integration between 0 to a, that is half of dx, minus integration of 0 to a cos 2 n pi x by a into dx. That's equals to 1. So b square remains outside, and here integration of 0 to a half dx, that will be giving the value of x between the x by 2 between the limits 0 to a, minus integration of cos 2 n pi x by l will be again here also we have the half, right? So half will remain. So here also, so half of integration of cos 2 n pi x by a will be sine 2 n pi x by a. Again differentiation of n pi x by 2 n pi x by a will be 2 n pi by a, and that's whole and solely equals to 1. And here we need to apply the limits, that is 0 to a. 0 to a are the limits, and when you apply the limit 0 to a, b square, so it will be a by 2 minus, and here you can observe when you apply the term 0 to a, so when you apply the condition upper limit a, and here anyway sine 0 will remain 0, when you apply the upper limit x will turns to a. When you apply a over here, a will get cancelled, and sine 2 n pi will always turns to 0. So this whole term will becomes 0. So b square of a by 2 minus 0, that's equals to 1. So whole and solely b square a by 2 is equals to 1, or b square is equals to 2 by a, or simply b is equals to square root of 2 by a. So initially we got the value of the arbitrary constant a, that's equals to 0, but there we didn't got the value of the constant b, and here we got the value of b, which is equal to square root of 2 by l. And now we can write the equation for the wave function of the particle, that is psi of x is equals to, that is b sine kx. The value of k is n pi x by a. This is the equation we got, and here we determine the value of b, which is equals to square root of 2 by l. Therefore psi of x is equals to square root of 2 by a, square root of 2 by a into sine n pi x by a. This is the equation for the wave function of the particle present inside the box. Hope you can observe. So this is the equation, psi of x is equals to b sine n pi x by a. So in the previous video we already observed this kind of equation where in case of sinusoidal wave equation, right? So the wave function as well the energy term also we determined. So in this way, the Schrodinger wave equation is useful in solving many quantum mechanical problems in order to get the energy, position, momentum. All these conditions can be easily determined with the help of Schrodinger wave equation. And that's about the application of Schrodinger wave equation for one-dimensional box. So if you feel the video is useful for you people, please do subscribe my channel, give like, share it and comment it, and press the bell icon to get the latest updates of my channel. Thank you.